Hello everyone, my name is Oleksii Mykhailenko. I am going to talk about modeling of cone crusher steady-state operation modes. Energy efficiency is a key factor that ensures favorable conditions for the recovery and future sustainable development of Ukraine. At the same time, mining and mineral processing plays a key role due to its high power intensity. Analyzing the energy component of mining production cost per individual processing stage, it can be found that the highest energy consumption has crushing and grinding processes. Therefore, energy efficiency growing can be achieved by improving these operations. There are two possible ways to do this. The first is the complete re-equipment of production lines with the latest equipment with high level of energy and efficiency. The second is to improve existing equipment and automated control procedures. The last way is more economically feasible, as it does not require large investment. At the same time, it's implemented if it's possible to identify reserves for improving energy efficiency. This is achieved by studying the steady-state operation modes of technological equipment. The purpose of this article is to obtain mathematical models of cone crushing steady-state operation modes, which can be used in the development of a control system for technological unit to determine the reserve for increasing energy efficiency, as well as its operating point and the limits of change in the main technological parameters. As a target of study of the steady-state properties of crushers, I choose a cone crusher with mantle width 2200 mm. The main purpose of the cone crusher is to reduce the lumpy material to the required size. Therefore, the main process variables that are controlled are product capacity and particle size distribution. There are a lot of input and output variables to control the crusher. The connection between them is shown in the function diagram of the unit. The input variables are feed capacity, the closed side setting, CSS, and the eccentric revolution speed. The disturbance is represented by a set of parameters that characterize the properties of the O. Percentage of the control particle size, hardness, fracture, moisture, etc. The output variables are product capacity, electric drive power, the wear of lining plates, and the amount of ore in the crusher. For the limited period of time, the steady-state model of the relationship between feed capacity and product capacity can be represented by linear dependence. The figures in slides show that as the ore hardness increases, if the feed is constant, the crusher product capacity decreases. Similarly, the CSS affects product capacity. Increasing or decreasing in the CSS leads to an increase or decrease in product capacity respectively. Next, we will consider the crusher steady-state model of the relationship between the feed capacity and electric drive power. Taking into account the closed side setting, it was determined that the power consumed by the cone crusher electric drive in the operation range increases with increasing feed capacity. It was found that the power consumption has a nonlinear dependence on the crusher product capacity for different values of the closed side setting. The steady-state characteristics based on equations from previous slide for the typical CSS values 5, 10 and 15 mm are shown in figures. At low feed capacity, the power consumption decreases with increasing closed side setting. Thus, the required product capacity can be achieved under any expected conditions. The next slide presents steady-state model for the relationship between product capacity and percentage of particle size class plus 20 mm for certain closed site setting values. The percentage of particle size class plus 20 mm as a function of crusher product capacity is shown in figures. The steady-state characteristics plotted according to equations from previous slide for typical CSS values are shown in figures. With the increase in product capacity, the percentage of particle size class plus 20 mm decreases. When the crusher product capacity is constant, the percentage of particle size class plus 20 mm is growing according to increasing CSS. The graphs also shows that at a low crusher capacity of the 310 ton per house, it's impossible to ensure the specified quality of the product. The influence of CSS on the percentage of particle size class is not as significant as product capacity, so adjusting CSS in range 5 to 10 mm can provide an acceptable crushed ore size when the product capacity change in the range from 320 to 330 ton per hour. At capacity above 330 ton per hour, the particle size distribution can be controlled by varying CSS in the full range from 5 to 50 mm. During the operation of the crusher, the liners of the concave and mantle and other elements wear out. The wear of the liners is essential to the product particle size distribution and power consumption. Equation 3 and figure A shows the dependence of the amount of crushed ore over the service life of the chamber liners depending on the product capacity on the intensity of mineral processing. The graph shows that with the increasing product capacity, the amount of crushed material increases during the period between lining replacements. When using magnesium steel lining, it can be assumed that with an increase in crusher product capacity, liner wear increase within the specified limits. This shows figure B. Proposed the mathematical description for analyzing the cone crusher steady-state operation modes based on experimental data from various sources. Multidimensional regression dependencies are determined, which allow us to establish the regularities of the iron ore crushing process. The input variables are the feed capacity and closed site setting. The output variables characterizing the quality of the process are product capacity, electric die power as a percentage of particle size class plus 20 mm. The model can be used to develop a cone crusher control system to determine the reserve for increasing energy efficiency, as well its operation point and the limits for changing the main process parameters. Thank you for your attention.